Built as the world's first commercial maglev, the Birmingham Air Rail link between Birmingham International Station and the airport terminal building was a tour de force of technology when it was launched in 1984, demonstrating the feasibility of maglev technology in a regular public capacity. Sadly, rising operational costs caused by the increasingly outdated technology behind its operation meant that by 1995 the maglev was facing its demise, and since then the application of maglevs on a widespread scale, as proposed alongside the original air rail link in the 1980s, has failed to come to fruition. The maglev, as derived from the term magnetic levitation, is a system of rail transportation where rolling stock is levitated by electromagnets, thus meaning that, in comparison to conventional railways, higher top speeds, superior acceleration and deceleration, lower maintenance costs, improved gradient handling, and lower noise can be achieved, but at the cost of construction expense, energy consumption, and the need for bespoke infrastructure. The first maglevs were conceived as far back as 1912, when French-American inventor Émile Bachelet demonstrated a model train that was propelled by electromagnetic levitation, though despite Bachelet filing a patent for the maglev technology, it wouldn't be until the 1960s that the application of such a form of rail travel would re-emerge in the United States, Japan, Germany, and the Soviet Union. Great Britain would also be involved in the development of alternative means of rolling stock and infrastructure, with one of the major projects for the period being the hover train, which took on a design similar to that of maglevs, and proposed the incorporation of hovercraft technology into a guided vehicle that could travel at speeds of up to 300 miles an hour, and therefore complete the core London to Glasgow run in as little as 2 hours. On February 7, 1973, Research Test Vehicle 31, also known as RTV-31, undertook its first flight and achieved a top speed of 104 miles an hour on the dedicated hover train test track in Cambridgeshire, though only a week after the completion of this first test run, all funding was halted and the project was unceremoniously cancelled, with the focus on speeding up passenger trains in the UK resting with the more conventional tilting train project of the Advanced Passenger Train, or APT. As for maglev technology in the UK, this wouldn't arise until the opening of Birmingham International Station on January 26, 1976, which was built to provide the first dedicated rail connection to the rapidly expanding Birmingham Airport in the West Midlands, and was situated on the Midlands section of the West Coast Main Line, 8 miles from Birmingham New Street. However, one glaring omission of the £6 million Birmingham International Station was a dedicated connection to the terminal buildings themselves, as while a covered elevated concourse was provided to link to the adjacent National Exhibition Centre, or NEC, which was opened on February 2nd of the same year, access to the airport itself came in the form of a bus link to the original terminal building. However, in 1980, an expansion plan to create a new terminal building at the airport was approved at a cost of £62 million, part of which would include accommodation for a dedicated connection between the train station and the new terminal, with initial feasibility studies starting in 1979 by the owners of the airport at the time, the West Midlands County Council, with decision-makers being opposed to the construction of a conventional railway to meet this need. Original concepts were for a long-distance rapid transit connection between Birmingham Airport and the city centre, initially with wheeled vehicles and later a maglev alternative, but following the feasibility study, the council had grave reservations as to the cost and the visual intrusion of the guideway, though in principle, the maglev solution had shown considerable benefits over and above the wheeled vehicle system. The study had concluded that the track was cheaper by 25 to 30%, and the running costs of the maglev vehicles were predicted to be over 30% lower due to the reduction of moving parts, while reliability was deemed to be very high, and it could operate in all weathers since there was no vehicle-to-track friction requirement. These facts prompted British Rail to continue the development of a maglev system as a joint venture with the Department of Transport, with it being envisaged that the benefits identified would lead to a cost-effective means of linking Birmingham Airport's train station and the National Exhibition Centre with the terminal building. The basic specification, not just for Birmingham but for all people mover systems of the type envisaged, would be for a small vehicle carrying 30 to 50 passengers running in all weathers under fully automatic control at speeds of up to 30 miles an hour, while the guideway supporting the vehicle would be designed so that it could be elevated or constructed at ground level. This simple specification meant that differing forms of magnet configuration could be chosen, including repulsion systems and attraction systems, with high-speed rail systems favouring a repulsion system, as it offered a number of benefits, not least being the very large air gap of up to 118 inches at which such systems can work. In order to achieve the large flux densities required, however, superconducting magnets would be generally necessary, and the vehicle would then become very expensive, which was more suitable for long-distance high-speed maglevs, as per the later Shanghai and Transrapid maglevs, but not for low-speed, high-frequency systems like the one proposed at Birmingham Airport. Instead, the attraction solution was considered more appropriate for low-speed operation, as while a permanent magnet solution could have been achieved, this would also have been expensive, while also requiring additional control means. The attraction method offered the most advantages to this type of vehicle, with a DC electromagnetic pulling upwards to a steel rail being specified, and could have been arranged so that the flux path was transverse or axial to the direction of travel, but the choice between the two had the potential to be complicated, with weight, track costs and suspension stiffness being elements in the judgment. The axial flow solution was chosen for the Birmingham vehicles, and magnets were designed that used approximately 2 kilowatts for each ton of lift, with the choice of whether the vehicle was above or below the track being decided on safety and cost grounds, which would comprise as small a track as possible with the vehicle above it, and the magnets wrapping around the track in order to pull up to the steel rails. In this regard, the system would prove to be incredibly safe, as beyond a structural failure of the guideway itself, the vehicle could not accidentally be derailed, and should the suspension system have failed, the vehicle would have become seated on skid pads that rub on the top surface of the rail and stop the vehicle, while in the center of the track, the reaction plate for the linear induction motor would be located and would ensure that the vehicle was independent of friction between the vehicle and the track, and contributed in a major way to the all-weather capability of the vehicle. The characteristic of the magnet, in terms of load against gap, was such that as the gap increased, the load which it would support decreased, and as the magnets to be employed were electromagnets, the current could be increased to raise the load-carrying capability, thereby meaning that through controlling the current, it would be possible to achieve a stable situation, with the magnet operating at a defined air gap and supporting a load. This performance could also have been improved by the conventional technique of adding damping, though this would result in an unsatisfactory control, as the stability and the gain of the control system were inseparable, while additionally, the control system could not provide a good suspension for the vehicle, as with this being a passenger-carrying service, magnetic suspension would lead to certain frequencies of vibration that would be uncomfortable for the travellers inside. Therefore, to match this passenger requirement, a natural frequency of suspension of 1 to 2 Hz was found to be ideal, with any higher frequencies being well attenuated, though the magnets on the vehicle could only operate with a small air gap, and thus it was important that both load changes over a long period and short duration, together with large force inputs, both of which would normally cause large displacements, were taken care of at the early stage. Similarly, as the guideway inevitably contained roughness at all wavelengths, the magnet and vehicle would follow the long wavelengths, but not all the short wavelength imperfections that may occur on the rail, as this would otherwise cause the ride in the vehicle to be too severe, and in order to meet these requirements, a complementary filter control system was developed, which, at frequencies below 2 Hz, would see the vehicle operated in such a way as to control the gap variation between the magnet and the rail. This would be achieved by filtering the gap signal with a low-pass filter, while at higher frequencies, the vehicle would be controlled to absolute displacement, or would attempt to follow a straight line in space, with the high-pass filter being an exact complement to the low-pass filter, in that their sum would always result in unity, and the stability of the system would be divorced from the ride quality. The gap variation in vehicle acceleration on a given track at a given speed would vary as the filter frequency changed, with an achievable value of 2 Hz being a satisfactory acceleration level of 4.5% RMS or root mean square, while the lateral performance of the magnet was much easier to control than the vertical, due to the magnet being given the correct characteristics at the design stage. Ensuring a proper relationship between the magnet pole width of 19 inches and the air gap, a natural frequency laterally of about 1.5 Hz could be achieved without the need for control action, with it only remaining to add damping to the lateral motion, which was obtained by arranging to have 2 magnets at each corner of the vehicle, which were offset by 4 inches from each side of the rail centre line, and were controlled differentially so that their vertical force was constant while producing a net lateral force. The lateral force would then be controlled to be proportional to absolute lateral velocity in order to give the lateral motion damping, with the lateral velocity being derived from a lateral acceleration measurement that in practice would see the control of the magnets be carried out modally, so that the natural movements of the vehicle, such as bounce, pitch and roll, were controlled individually. Based on the initial studies, a successful prototype vehicle was built and tested at the Railway Technical Centre in Derby, but in order to build and install the system at Birmingham, British Rail and the West Midlands County Council prompted the formation of the People Mover Group under the management of John Lang, which was backed by several major British companies, including Balfour Beatty, who was responsible for the civil engineering work, Brush Traction, who supplied the traction control equipment, and Metro Camel, who assembled the vehicles, all of whom answered to GEC transmission and distribution projects, who not only provided the power supply hardware, but also maintained overall project management, while British Rail provided R&D support. The 0.3-mile-long double track closely resembled the originally envisaged midi-tram concept of 1979, with the basic structure being of concrete, and was designed to take the dead loads of the fully elevated track, the active load of the vehicle, which was well distributed by the length of the magnet poles, and the emergency loads caused by vehicle delevitation, with the latter proving most difficult to incorporate, as there had to be some design interaction between the expected flexibility of the track and the maximum vertical load seen under emergency conditions. The overhead structure would sit on piers that were spaced 40 to 50 feet apart, and supported by precast longitudinal track beams and side beams, with the track beams and side beams being tied together by cross beams at approximately 8-foot centres to ensure that the loads were properly shared by the structural elements, with these beams being substantial and rigid so that dynamic interaction with the vehicle control system was minimised. On top of the track beams would sit galvanised steel sleepers at around 3.2-foot spacings, which would support the rails at a gauge of 4.7 feet, with the rails, to which the magnets attract themselves, being constructed from standard rolled steel sections that were galvanised and painted, with the provision for expansion also being built into the design, together with flux bridges to minimise the disturbance to the vehicle at joints in the rail. The rails themselves would be laminated to reduce lift losses due to eddy currents, but their alignment specification was not stringent, and could have been compared to that for a secondary railway line, while in the centre of the track would be the linear motor reaction rail, which was formed of a steel T-section with an aluminium extrusion clipped to the top flange. A Melinex sheet separated the two in order to avoid corrosion, and relative movement was possible to allow for expansion, with two electrical conductor rails being mounted alongside the reaction rail beneath the sleepers in order that power could be picked up by the vehicle, while a 600-volt DC system would be employed to power the trains, and between the two guideways sat a walkway for passenger evacuation in the event of a breakdown. The stations at each end of the track employed a central platform, while sliding doors at the platform edge prevented access to the track, but opened simultaneously with the vehicle doors when it was stationary, while the vehicles themselves would have all structural loads be carried in the aluminium chassis, which was of a welded construction and weighed 0.8 tons, which comprised 16% of the vehicle tare weight. Most of the electrical equipment was housed in compartments within the chassis, in a manner that allowed for easy maintenance access from the side of the vehicle, while the duplicated heating and ventilation equipment was located above the floor under the bench seats at either end of the unit, and the linear motor was mounted on beams which were resiliently connected to the vehicle and stood above the emergency skid pads. This arrangement enabled the designer to mount the motor flexibly to the body, whilst avoiding the motor striking the track in the event of an emergency delevitation, while a single-sided axial flux short-stator motor with blown cooling was used for traction and braking, together with a three-phase motor being employed, as formed through a 7-pole field winding embedded in slots of a laminated steel core. This motor could produce 4 kilonewtons of thrust up to the desired speed of 33 miles an hour at the working air gap of 7 inches, with this being achieved through a 240 kilovolt continuous rating, 3-phase variable frequency and voltage inverter, which accepted a pulse-width modulated signal from the controlling microprocessor and produced a motor current waveform with a low harmonic content. The inverter, which operated over the frequency range of 0 to 45 Hz, was naturally cooled by airflow over externally mounted fins, while the magnets comprised large E-core devices constructed of steel with aluminium foil windings, as carried over from the British Rail prototypes, with thermistors being inserted into the windings so that excessive internal temperatures could be detected. The suspension control system had inputs from 3 types of transducer, which were all selected for their reliability, and the magnets operated with a nominal air gap of 0.5 inches, though this was reduced to 0.1 inches in the stations in order to reduce the duty of the magnets in raising the laden vehicle, while at the 0.5-inch hover height, the air gap flux density was 0.8 Tesla. The magnets and the choppers that drove the vehicle would be continuously rated for 25 ampere, and had a peak capability in excess of 75 ampere, with the choppers being naturally cooled, and used 4 power transistors and freewheel diodes to form a pair of 2-quadrant bridge circuits, each switching at 1 kHz in antiphase. The choppers produced the precisely controlled DC current for the magnets, the magnitude of which could be rapidly changed, while the passenger compartment of the vehicles were constructed in fiberglass, thus permitting the designers the ability to achieve minimum weight, while at the same time allowing a freedom for styling, with this compartment being suited essentially for standing passengers, although bench seats were provided at each end. In all, the tare weight of the total vehicle came to 4.8 tons, and the overall dimensions of the vehicle were 19 foot long, 7.3 foot wide and 9.8 foot high, and were generously provided with windows and a pair of large automatic sliding doors on one side of the car that allowed for rapid passenger entry and exit. In terms of control systems, the Birmingham Airport Maglev route would comprise 4 independent but connected systems, with the first being the Automatic Train Protection or ATP system, which dealt with all safety functions and monitored the operation of the vehicles, while the second system carried out all of those functions normally attributed to the vehicle driver and was dubbed the Automatic Train Operation System. The line supervision system enabled the system operator to observe and interact with the previous 2 systems as necessary, while the radio communications system allowed speech communication between the operator and the passengers, and was used for routine and emergency instances, with the vehicle normally being under the control of the ATO system. At the stations, the vehicle communicated with the line supervision system by means of a local data link, with various exchanges of information including both vital and non-vital messages relating to the vehicle alignment and the coherent operation of the vehicle in the station doors, while the vehicle fault status was also passed to the supervision system, and the journey parameters for the next trip were given to the vehicle if the operator required changes. As the vehicle departed the station, it maintained communication through a continuous inductive data link, with its cables transposed at intervals, and enabled the ATO system to know the precise position of the vehicle, with the speed control then being adjusted so that the vehicle followed a predetermined speed profile, which could be continuously measured by a Doppler radar speedometer. The ATO computer also monitored any passenger emergency signals, the levitation system, the doors, and auxiliary systems, and it was possible to control the vehicle manually through the ATO computer in an emergency or for maintenance purposes, with all of the functions of the ATO being monitored by the ATP, though this system had an additional safety input through passive markers positioned at frequent intervals along the track. The ATP monitored the passing of these markers, and in the event that a marker was not seen within a time limit either side of the target time, normally 1 second, the system would declare an emergency and stop the vehicle, with all of the ATP functions being achieved using fail-safe electronics and vital railway signalling relays, though extensive use was made of modern digital techniques for non-vital functions. At a cost of £3 million, which was incorporated into the £62 million construction cost of Birmingham Airport's new terminal, the Maglev system was erected from the terminal buildings to Birmingham International Station, with the People Mover Group paying half the cost of the project, while the Department of Trade and Industry contributed a £325,000 grant. Metro Camel, meanwhile, was tasked with developing and delivering the Maglev vehicles at their Washwood Heath factory in Birmingham, though during the construction phase of the system, several difficulties were encountered, one of which being due to the fact that there was no contact between the concrete guideway and the trainers, thus meaning conventional speedometers would not function. Another major setback came out of a decision made by one of the companies to reinforce the bottom of the carriages of an early train with an additional layer of fiberglass, which increased the structural strength of the vehicle, but at the same time increased the overall weight of the train, which was already relatively heavy, and meant that the electromagnets were unable to relatively keep the train afloat, thus requiring a new train to be produced to replace it. Finally, on August 16, 1984, Her Majesty Queen Elizabeth II inaugurated the Birmingham Airport Maglev link, with this system being able to whisk passengers in around 90 seconds between the railway station and the terminal building, and had a theoretical maximum capacity of 3,200 passengers per hour in either direction, which were carried in a pair of twin carriage trains that could accommodate up to 80 passengers at a time. Despite the complexity of the project, few operational problems were encountered, though an inevitable series of teething issues did arise early on, including a couple of delevitations and troubles with the ATO system, while similar minor adjustments were necessary to the emergency brake pads, though after tests on various materials, pads fitted with the most suitable type were installed. Initially, only 2 vehicles were provided, whilst a third was installed following proving trials in 1985, with the passenger carrying capacity eventually reaching 120 passengers once it had been proven that these units could operate in multiple, while in September of the same year, the route was handed over from British Rail to Birmingham International Airport Limited, who would continue to operate the system for the next 10 years. From here, the Birmingham Maglev would operate dutifully and without major incident until July 1995, at which point Birmingham International Airport, citing the high cost of maintenance and repair, chose to abandon the Maglev system, with the service between the terminal and Birmingham International Station being replaced instead by a bus service, while the redundant Maglev vehicles were placed in store at the airport. As for the Maglev technology behind the Birmingham system, though it was proven to be a reliable and functional technology that worked for years in the relatively simple employ of an airport shuttle, British Rail's research departments were unable to sell this system onto the export market, with its systems and hardware being heavily outdated by the mid-1990s, at which point German alternatives such as Transrapid had taken the lead in maglev technology. Ultimately, in December 2000, it was decided to replace the former maglev shuttle with a cable shuttle, which would repurpose the abandoned guideway of the maglev, with Austrian firm Doppelmayr being awarded the contract to supply the system, which comprised a double-track route equipped with fully automated twin-car units that would take 90 seconds to complete the journey. The new Birmingham Airlink service, initially known as Skyrail, would be formally open to the public on March 7, 2003, having cost £11 million to complete, and was delivered in conjunction with the £7 million transport interchange at the railway station itself. On a global scale, maglev technology would never be adopted in the widespread manner hoped by its progenitors, with the most successful commercial system being the Shanghai Maglev of October 2003, which was developed by Transrapid and operates between central Shanghai and the Pudong International Airport at speeds of up to 268 miles an hour, though other systems do exist, primarily in China, Japan and South Korea, such as Beijing's S1 subway line, the Incheon Airport Maglev, and the under-construction Chuo Shinkansen between Tokyo and Nagoya. As for the vehicles, all three survive in preservation, with a model of the Birmingham Maglev, together with carriage number 3, being held at the locomotion venue in Shildon, while car number 1 resides at Railworld in Peterborough, and car number 2 was sold at auction in late 2010 for £25,100, with the proceeds to go to 2 charities, but the bidder defaulted, and it was later resold to a private buyer near Kenilworth for just £100. In the end, the Birmingham Maglev proved to be an interesting but often overlooked pioneer effort by British Rail to develop the concept of commercially viable maglev technology, and while its overall applications were limited, and its system confined merely to the role of an airport shuttle, the maglev train proved itself a reliable and functional means of transportation for over a decade, while also delivering a hint of the cutting edge to the regular passenger market.